Hello, this is Dr. Gardner. Today we're going to be talking about gases and recognizing how volumes of gases relate to the number of gas particles that we're maybe looking at, or the number of grams of gas particles we may be looking at. We're going to look at a few examples with respect to gases in balloons, as well as we're going to start looking at the partial pressure of gases, that meaning in a mixture of gases, what is the partial pressure exerted by each component gas on the total pressure in its container. Now, with respect to two balloons, let's say we have a carbon dioxide containing balloon, so carbon dioxide gas in the orange balloon, and oxygen gas in the yellow balloon. If I look at these two balloons, if they have the exact same volume, then we can think about the gas molecules contained in both balloons. Now, if they're acting as an ideal gas, then the identity of the particles that exists in the gas phase really doesn't matter. It's related more to the number of particles that is in the gas balloon with respect to the volumes that we might have or the pressures that we might have. And so in this case, if I were to ask, well, which one of these balloons have the greatest number of gas molecules? Well, if they're at the same temperature and pressure, then I should have the same number of moles of gas in both of these balloons. And so I would expect that the number of gas molecules should be equal or identical in the two balloons, because the identity of the gas particles shouldn't matter if they're acting ideally, because we're ignoring any attractions between the individual gas particles. We're assuming the gas particle's volume is so small that we're ignoring it in our calculations with respect to the entire volume of the gas because of all the empty space between the particles. Okay, now if we then ask ourselves which balloon has the greatest number of moles of gas, well, if the number of particles are equal, the number of moles should be equal as well. And if we ask ourselves then, well, what's the mass in both of these balloons? I want you to think about this. So which of these balloons do you think would have the greatest mass? Now be careful, just because they have the same number of particles and the same number of moles of the gases doesn't necessarily mean they have the same mass, because carbon dioxide's molar mass is about 44 grams per mole, whereas diatomic oxygen's molar mass is about 32 grams per mole, right? Because there's two oxygens in the molecule. So there is a different mass per particle in each case and a different mass per mole of the gases in each case. So the higher molar mass gas has the largest grams in the container of the balloon. Now, if we consider the balloon's density, well, density is going to be mass over volume. So I'm thinking, okay, well, if I'm looking at mass over volume, well, the balloon's volumes in both cases, we're assuming that the volume of the balloon 1 here that's orange is equal to the volume of balloon 2, which is yellow. So if the volumes are the same, but I have a molar mass of 44 grams per mole for carbon dioxide and 32 grams per mole for oxygen, there's a larger mass per volume for the carbon dioxide balloon, so its density would be the greatest. Okay, so the CO2 balloon has the greatest density in this case. Okay, so make sure you feel comfortable with making those types of predictions as we're looking at volumes of gases in laboratories as well. So let's say we have two yellow balloons, so they both contain oxygen gas, but one has a greater volume, the other one has a smaller volume, but they're at the same temperature and pressure. If I looked at these two balloons, let's make some predictions about the smaller balloon here, which would have the, in this case, would the oxygen in the smaller balloon have more or less particles than the oxygen in the larger balloon. Now we're assuming they're at the same temperature and pressure, so we're not changing those variables. So now we might be looking at the different numbers of particles or different numbers of moles of particles. So the smaller balloon should have the smallest number of molecules, and that means it should have the smallest number of moles of oxygen gas. And the mass here, well, the molar mass is the same in both cases, but if I have fewer moles of gas in the smaller balloon, then the mass of the gas in the smaller balloon should also be smaller. However, the density, remember my density was that mass over volume ratio. So as I ended up with the volume of the smaller balloon being less than the larger balloon, well, the mass decreased as well, but the ratio of mass per volume would be the same. So there's the same density in both of these balloons because the particles are identical, and I have fewer particles, but I also have a smaller volume. So I still have that same ratio, the same density in both cases. Okay, so hopefully this has you thinking a little bit about volumes of gases and the number of particles or moles that we might have. Now let's think about a slightly more complex scenario. What if we think about the number of particles that we have in a balloon that contains a mixture of gases. Now, if I have a mixture of gases, well, the identity of the gases, if they're acting ideally, doesn't really matter. Every single gas in that mixture, all of its particles are contributing to the overall properties of the balloon. So they would be contributing, for example, to the overall total pressure being exerted against the walls of the balloon. So every single gas particle has an equivalent amount of contribution, on average, to the overall pressure of the balloon itself. So I can go ahead and think about this. I can say the total pressure. So we're going to use a law called Dalton's Law of partial pressure. So the total pressure of all gas particles in the balloon is being exerted by, let's say, gas component A. So gas A will have collisions with the walls of the balloon and contribute part of the total pressure. So we're going to say that's a partial pressure due to the first component in the mixture. Then each other component in the mixture. So gas B, all of its collisions will exert part of the total pressure. So it has a partial pressure that adds up to the total. And so every component, no matter how many gas components I have, will have a contribution of a partial pressure that I sum up to be the total pressure of all gases against the surface of that container. So let's say we had nitrogen gas and oxygen gas in a container. Well, the total pressure exerted against the walls of this container would be due to the partial pressure of my nitrogen gas and the partial pressure of my oxygen gas, and both of these gases being in the same container should be at the same temperature, and so their average velocity of the particles should still be the same. So if I'm thinking about this, which of these two gases would exert a greater partial pressure? Well, it would be the nitrogen gas, because there's more nitrogen gas present in the mixture, a larger percentage of it. So the partial pressure of nitrogen should be the largest. The partial pressure of the oxygen gas, since there's fewer particles per volume, should provide the smaller partial pressure. Okay, but both of their partial pressures, both of their collisions of nitrogen gas against the walls of the container and oxygen gas against the walls of the container will contribute to the total pressure. Remember, pressure was force due to those collisions over the area that they're being exerted against. Okay, so let's compare this to how you might be collecting gases in the laboratory. So if I'm collecting gases in the laboratory, well, I could go ahead and have a container where a reaction's occurring, and I could collect gases over water. Now, what I could do here is, let's say we had this bottle of water in this water bath, and we could have filled this container full of water and inverted it in the water bath so there was no air inside. Now, in the laboratory, we often will use a graduated cylinder. We will go ahead and fill the graduated cylinder full of water, and then we will go ahead and invert the graduated cylinder in the water bath. The advantage to this is once we start collecting gases, we can measure the scale on the inverted graduated cylinder to see the volume of gas collected. Okay, so here, this reaction is potassium bromate. I'm heating it up until I cause it to decompose. Now, I know this is a decomposition reaction because I have one compound forming two products, the potassium bromide and the oxygen gas. So the solid that's left behind at the end of this reaction inside of the test tube would be the potassium bromide. I'd want to keep heating the potassium bromate until I no longer saw gas evolving and I didn't see any more bubbles of gas bubbling through the tubing into my inverted glassware. Now, the bubbles of gas is oxygen gas is identified by this reaction. Now, many times in the laboratory we might be collecting hydrogen gas. It all depends on the type of reaction you're performing. Now, as I'm collecting the bubbles of gas here, what happens is they will produce a volume of gas in the inverted container, which will force water out of the inverted bottle here, or an inverted graduated cylinder. And what I want to do is level the height of the water with the water in my inverted glassware so that I have the total pressure inside and outside of my glassware being the same. So the atmospheric pressure pushing down on the pool of water should be the same as the pressure due to gases collected inside of the glassware. Okay, so the total pressure inside and outside should be the same. Okay, so we're going to use Dalton's Law of partial pressure here to think about the inside of our container with the mixture of gases collected. Now, most of the gas that I've collected here would have, in this example, been oxygen gas. In our gas laws laboratories, we usually collect hydrogen gas, though, so that would be the component gas that you'd be solving for there. Now, my total pressure, though, would be due to all the gases inside of the glassware. So I would have my total pressure being equal to the partial pressure of the oxygen gas collected, but I also have the liquid that I'm collecting the gas over. In this case, I'm collecting the oxygen gas over water. So I'm going to end up with the vapor pressure of the liquid, which is water vapor here, exerting part of the pressure. What that means is some of my water molecules present in the liquid state, some of it is evaporating. There's a small amount evaporating until I end up with a water vapor pressure due to water molecules in the gas phase also colliding with the walls of the container. Now it should be a minor component of the total pressure. The major component with respect to the total pressure should be the oxygen gas, which would be present in larger quantities. So this will be the largest partial pressure in this case. But I still need to correct for the water vapor pressure because it will exert enough that if I ignore it, I will end up having a somewhat significant error to my calculations. In fact, if I were to calculate the moles of gas that were in the container with respect to a total pressure, it would be the moles of the oxygen gas plus the moles of the water vapor. I want to find just the moles of the oxygen gas. So I'm going to go ahead and solve for that by subtracting water vapor pressure from both sides of my calculation. So if I take the total pressure here, subtract the water vapor pressure from it, we should end up with the rest of the pressure being from the oxygen gas that we collected. Now we are assuming that you didn't have any significant amount of air inside of your container when you started, or you'd end up with a little bit of other gases from the atmosphere, such as the major component being nitrogen gas, present exerting part of the pressure as well, which would throw off your results just a small amount. So try to make sure that you have very little, if any, air inside of your inverted glassware when you first begin. Okay, so let's think about where we can get the total pressure. The total pressure here can come from the barometer. So if I look at the atmospheric pressure, the pressure total being exerted against the water is going to be from my barometer in the lab. So I can read like a mercury barometer, or I can have my lab instructor find the total atmospheric pressure that day for me. That barometer pressure is often measured in millimeters of mercury, but sometimes we might report it in torr. Be careful what scale you look at on the mercury barometers, because you could also have inches of mercury. So you want to make sure you use the correct scale with respect to taking the reading. We usually want to work with millimeters of mercury rather than inches of mercury, though you could potentially convert either value. With respect to the gas collected inside of the container, well, the pressure there is due to water vapor as well as the oxygen gas, but its pressure total should be equal here to the atmospheric pressure as long as my height of liquid inside and outside the container are at the same height, so I don't end up with a column of water exerting pressure. Okay. Now, the water vapor pressure, if I want to find out what that value is, since I'm getting the total pressure from the barometer, well, the water vapor pressure is going to come from a table of partial pressures of water vapor at a specific temperature. So I can look that up, and in fact I'm going to show you the table here. And laboratory temperatures usually range between roughly maybe 18 to 25 degrees Celsius, depending on how cool or how warm your laboratory is. And so let's say that our laboratory was at 23 degrees Celsius for the temperature. If I looked up the water vapor pressure on our table, we'd find that was 21.1 torr. And realize my torr's values would be the same as my millimeters of mercury for the sake of this calculation. So I have 22.1 millimeters of mercury. Now at sea level, my atmospheric pressure would be 760 millimeters of mercury. So I know this water vapor is only contributing a small amount of my total pressure, even at higher elevations. Okay, so let's go ahead and use this information to solve a problem. We're going to have a slightly different temperature. I'm going to use 18 degrees Celsius for this next problem. So if I was working with 18 degrees Celsius, I'd use a partial pressure for the water vapor of being 15.5 millimeters of mercury. Now when I find these pressures, if I want to find the moles of gas, I'm going to have to use the ideal gas law equation. So if I think about the ideal gas law constant, what pressures do we have in the units of the ideal gas law constant? Hopefully you remember that we were working with atmospheres, so I'm going to have to convert my torr at some point to atmospheres before I use them in my equation. Okay, so first of all, let's say that we collected hydrogen gas in the laboratory. So I could use an alkali or alkaline earth metal, react it, let's say, with an acid in the laboratory that would produce hydrogen gas as I form a metal oxide or a metal hydroxide. And that hydrogen gas we could then collect, let's say, in an inverted graduated cylinder. So I collect, let's say, 2.25 liters. If I was really collecting that amount, I'd probably use a different piece of glassware than a graduated cylinder, but if you had a smaller volume, a graduated cylinder would do the job nicely. We could collect that over water. So since I'm collecting the hydrogen gas over water, I'm going to have some water vapor pressure. I'm going to have the vapor pressure due to my solvent, or my liquid that I'm collecting it over in this case. And the temperature I collected it at in the laboratory was 18 degrees Celsius. I go to the barometer and I read that the total pressure of the atmosphere from the barometer was 722.88 torr, but I'm thinking in my head I'm going to have to convert this to atmospheres, or I'm going to have to find the partial pressure of the hydrogen gas and at least convert it to atmospheres. Now my degrees Celsius, if I think about my gas law constant has units of Kelvin. So I'm going to go ahead and have to convert the degrees Celsius to Kelvin at some point here as well. So I'm thinking that in my head with respect to some units. The liters is perfect. I have units of liters for volume in my gas law equation, so that one wouldn't have to be converted. But if it was milliliters, I would have to convert from milliliters to liters. Frequently when students perform the gas laws lab, they forget to convert from milliliters to liters, so don't forget to do that. Okay, now let's talk about how many moles of hydrogen gas are produced in this reaction. In order to find that, I need to find out the partial pressure due to the hydrogen gas collected. So I'm going to have to correct for that by also thinking about the water vapor's partial pressure for my table that I looked up. Okay, so here's the facts that I know for this problem. My volume is 2.25 liters. My temperature was 18 degrees Celsius, but I want to convert to Kelvin, so I add 273.15 Kelvin to provide 291.2 Kelvin for my temperature in Kelvin for the room. I don't know the number of moles of the gas, but that's what I'd like to solve for in the end here. I go ahead and look up my table of partial pressures, and I find for the 18 degrees Celsius, as we mentioned earlier, that my partial pressure is 15.5 torr. Okay, so my partial pressure of the hydrogen gas. So realize my pressure total for my Daltons Law of partial pressure will be equal to the partial pressure of every gas in the mixture. Now I'm assuming that I have collected hydrogen gas in this case over water. So I have the partial pressure of the hydrogen gas, and I'm assuming the only other gas that's present inside of my container is water vapor. So I have the partial pressure of water vapor that I must also account for, but we just looked that up. So that partial pressure of the water vapor was the 15.5 torr. The total pressure that I looked up from the barometer was the 722.8 torr. So my unknown pressure was the partial pressure of hydrogen gas. So I went ahead and subtracted the partial pressure of the water vapor from both sides of my equation. So I isolated the unknown variable of the partial pressure of hydrogen gas is equal to my total pressure from the barometer minus the partial pressure of the water vapor. Now I want to make sure the units are the same. So I looked up torr for my partial pressure of the water vapor and torr from, let's say, the barometer, or these could have been in millimeters of mercury, or I could have converted them to atmospheres. As long as I'm consistent with my units right now, I'll be in good shape. So if I go ahead and take the total pressure from the barometer of 722.8 torr, subtract the water vapor pressure of 15.5 torr, I find that the rest of the pressure exerted by the gases in my container must be 707.3 torr. And we're assuming that's equal to the only other gas component that I'm collecting, which should be the partial pressure of the hydrogen gas. Now I want this partial pressure of the hydrogen gas because I'm going to use it in my ideal gas law equation next. If I use the partial pressure of the hydrogen gas in my ideal gas law equation, I can solve for the moles of the hydrogen gas. If I were to accidentally plug in the total pressure of 722.8 torr, I would accidentally be solving with the ideal gas law equation for not just the moles of the hydrogen gas, but I would also have mixed in there the moles of the water vapor pressure. Right? So I'd end up with the moles of the water vapor as well. So that wouldn't really be the answer I'm looking for. That would be both components in the gas phase moles if I use this pressure. By using the partial pressure of the gas, well then I solve for the question that was asked, which was the number of moles of hydrogen gas produced. Okay. One last calculation. Accidentally wrote over it. Apologize for that. I had 707.3 torr for the partial pressure of the hydrogen gas. I just converted that to atmospheres. So I divide by 760 torr for 1 atmosphere. So I end up with this partial pressure for the hydrogen gas related to atmospheres being 0.931 atmospheres. I want atmospheres, again, as I said before, because my ideal gas law equation constant is in atmospheres as well. Okay, so let's go ahead excuse me, let's go ahead and let's solve now for the number of moles by using the ideal gas law equation. If you haven't used the ideal gas law equation before, you'll want to look at my last tutorial video on gas laws. But what we can realize here is we know the volume in liters, 2.25 liters. We know the gas law constant has units of liters, so my units are matched. My temperature is 291.2 Kelvin, so I've matched my units of Kelvin. So I want to make sure that I matched all of my units in order to cancel units correctly. I'm going to solve for the number of moles of gas, so I'm going to end up with units of moles for N at the end of my calculation. My partial pressure of the hydrogen gas, I want to be very careful that I am using the partial pressure here and not the total pressure, is 0.931 atmospheres. You want to make sure you've matched your units of atmospheres with the gas equation constant. Now that we've matched liters, atmospheres, and Kelvin, we should be in good shape. Now I want to remind you that if you had measured the volume of gas in milliliters, which we often do in our laboratory using a graduated cylinder, you would have to convert from milliliters to liters for your units before you use the ideal gas law equation. Okay, and students will often forget this, so they will forget to convert from milliliters to liters and be off by a factor of 1,000. So be very cautious. You're keeping track of all of your units carefully. If you're always writing down your units with every number, this shouldn't be a problem. However, some of you get in bad habits of not writing down units, and that's where you end up with trouble. Okay, so if we use the ideal gas law equation, remember that's our Pivnert equation, right? Pressure times volume is equal to the number of moles times my gas law constant times my temperature. So if I solve for N, my number of moles is just determined by dividing both sides of my gas law equation by my gas law constant and my temperature to algebraically solve for N. So I'll find that my number of moles is equal to my pressure times my volume over my gas law constant over my temperature. So that's what I've written here. Number of moles is equal to pressure times volume over R and over my temperature. I make sure all my units match. So I take the partial pressure here, and remember we're using the partial pressure of the hydrogen gas, not the total pressure of the system. So I'm taking 0.931 atmospheres for the hydrogen gas partial pressure. It's an atmosphere, so it'll cancel my units in my ideal gas law constant. I'm multiplying by the volume of gas collected. I make sure it's in liters, so that will cancel the liters in my gas law constant. And I had collected 2.25 liters of the gas. Now my temperature I had converted to Kelvin, because then I can cancel Kelvin in my gas law constant, and my temperature in Kelvin for the room was 291.2 Kelvin. Okay, so I have units of moles left over in the end, which is what I wanted for N. So I would calculate 0.0877 moles of my gas collected. Now, if I wanted to convert to grams, I can multiply by the molar mass of the gas, but realize it is diatomic hydrogen that we're looking at here. So it would be 2.02 grams per mole roughly to 3 significant figures, so I'd have to multiply by 2.02 grams per mole. That would give me my number of grams of hydrogen gas collected if I were asked to do that. Okay, so what I recommend that you do with what we've talked about today is practice your homework problems related to Dalton's Law of partial pressures. Okay, make sure you start working on your laboratory calculations for the gas laws lab as soon as that is required. Okay, good luck everybody. Next time we'll be looking at how to apply gas laws to stoichiometric reactions. So chemical reactions involving gases. We'll look at the number of moles and the stoichiometry there. Okay, have a great day everybody. See you soon.